Okay, welcome everybody. I was just watching the participant numbers climbing there. So this is welcome from me, Tim Lenton and Patricia Pignot. We're going to jointly try and chair this event on tipping points, particularly the tipping element of the Amazon rainforest. So we're delighted to see so many people joining the webinar discussion. It's the second one we've had in a series discussing tipping elements in the climate system and abrupt changes in the Earth system. The general aim of our series is to advance knowledge on the tipping elements, support efforts to increase consistency in the treatment of climate tipping elements in the science community, generally develop a research agenda, and hopefully design some joint model experiments as part of something called a tipping element model intercomparison project, or TIPMIP. So we had an earlier webinar which was giving, back in September, a general update on climate tipping elements, and we'll try and post a link in the chat because you can watch it back on YouTube and stuff. We've got another webinar coming. We've definitely got one coming on the permafrost, and we'll post a link later about when and where to register for that. But yeah, the focus today is on the Amazon and its tipping points. And we're going to hear a couple of great presentations on potential tipping of the Amazon and forest dieback in particularly the perspective, well, hopefully from Earth system model runs, but also I suspect from data. So just before I hand to Patricia to introduce the speakers, I just want to kind of say a word or two about the three organizations that are supporting the discussion series and say thanks. So one of those is the Earth Commission, which is a global team of scientists who have the mission to define a safe and just corridor for people in the planet. I'm one of those, so that's great fun, and we're hard at work. The second organization is the Analysis, Integration and Modeling of the Earth System, the AIMS as it's called project, a global research network of future Earth. That's a bunch of Earth system scientists and scholars that are trying to develop innovative and interdisciplinary ways to understand the complexity of the natural world and its interactions with human activities. And then finally, the third key organization here is the Safe Landing Climate's Lighthouse activity of the World Climate Research Programme. And that's, looking for routes to a safe landing spaces for human beings and natural ecosystems in a changing climate, and exploring future pathways to avoid dangerous climate change, whilst also trying to meet the UN Sustainable Development Goals. So a couple of house rules. I think we're going to have a couple of great short talks. Whilst the talks are going on, feel free to pose questions using the Q&A feature, which you should be able to find at the bottom of Zoom there, and I'll keep an eye on those. And then we'll use those questions to inform the discussion session after the presentations. And for the dedicated, after we've had a 1 hour block of 2 talks and some specific discussion, the dedicated are willing to stay on for a more in-depth discussion for a further half hour. There's, as well as a chat box where you can make comments, there's also a Miro board that's hopefully getting linked in the chat while I say this. And there's a bunch of experts in the audience I can see. All right, that's enough for me. I'm going to hand over to Patricia to introduce our first speaker.
Hello, everybody. It's great to take part of this event and being honored to introduce these amazing scholars that will be bringing their expertise on Earth systems modeling in the focus on the Amazon region. So I couldn't be more happy. And also, of course, thanks to Caroline for organizing this whole event, the sponsor institutions, and also team for coordinating the moderation of this session. So our first speaker, then it's a pleasure to introduce Professor Carlos Nobre, who has dedicated his scientific career mostly to understand the Amazonian and climate science at the Brazilian National Institutes of the Amazonian Research, INPA, and also the Institute for Space Research, INP. He proposed almost 30 years ago the hypothesis of the Amazon savannization in response to the consequence of deforestation and climate change. So he's a former national secretary of the Research and Development Minister and Science and Technology in Brazil, also former president of our post-graduation program at the federal agency CAPES. He's presently a senior research working at the Institute for Advanced Studies at the University of São Paulo. So thank you, Carlos, for being here, and the floor is yours.
Thank you very much, Patricia. Good afternoon to all, team, Peter, all our friends for many, many years, decades. And thank you also for your work related to the Amazon. Let me share the screen. I will try to basically to make a summary. Basically, I'm not going to say whether I will respond to this question, yes or no. I think still open, but I think we are progressing, particularly looking at the data, not only models, but mostly the data that we are seeing unfolding in the Amazon. Just to start a very, very simple climate envelope, when we see here the forest, tropical forest, and the savanna, and you know, the simple climate envelope is the duration of the dry season. Anything longer than 4 months dry season, this is savanna. Shorter is forest. It's interesting that this area here, Eastern Amazon, has a longer dry season, but there is a forest here. And so many studies explain why we have a forest even with a longer dry season. Let's see here. Also, if you look at the greenness, the NDVI data, this is also very, very well known, a very important element when you don't see the seasonality. You see seasonality in the savannas here, in the north, in the south, but the rainforest is always producing photosynthesis. The net primary productivity is even higher during the dry season. This is unique of the tropical forest, particularly of the Amazon. More photosynthesis during the dry season. This is a recent summing up of the science panel for the Amazon. I think many of you participating in this webinar are members of the science panel for the Amazon, Herman Poveda and many others. And so this is just a summary of hundreds of studies based on observations. And summing it up, it's just millions of years of evolution of the tropical rainforest meant really the forest is very efficient in recycling water, deep roots, continuous evapotranspiration, as I mentioned before, higher evapotranspiration during the dry season. This is just opposed from the tropical savannas, when there is a very, very long dry season, very dry, and much less evapotranspiration. And very efficient recycling of water, maximum temperature 30 degrees, because of 70% of the net radiation goes into evapotranspiration. Volatile organic compounds produced by the forest becoming cloud condensation nuclei, very special evolution, very high biodiversity, which maintains also this the rainforest the way it is, with diversity. Of course, then there is this recycling of water. 28% of the rainfall is recycled, and then it's transported in this area by the aerial rivers and feeds the rainfall systems south of the Amazon basin. So this is evolution over millions and millions of years. And then in particular here, just want to say how important the deep roots are. You see here in the wet season, 68% of the water removal is up to 3 meters. But when you go to dry season in this area in Eastern Amazon, when the total rainfall is about 1.8 meters, so it's a drier portion of the Amazon, but the withdrawal of rain goes to 7 meters, 84%. Just to say how over millions of years, the ecosystems, there is over 16,000 different tree species, the highest tree species diversity in the planet. And so that just to show how that evolved and why we have such a large rainforest. But of course, in the last 50 years, it's a lot of deforestation. We have now 17% of the forest clear. There are some areas which were abandoned. There is a regeneration, but this is the total, more than 1 million square kilometers, mostly over eastern, southern Amazon and also near the Andes. So this is 17%. And also more and more, what really many models in the past we did not take into consideration, but certainly now we have to take into consideration in the new models. As Tim mentioned, planning for an intercomparison to find out how models will predict the tipping point would be very important as outcome of these meetings and many of other meetings. But we have to start really taking into consideration the forest degradation. In past experiments, we only removed the whole forest and see how the atmosphere would respond. But in fact, we have 17% of areas in the Amazon which are degraded. Like, you have here, you start with selective logging, you have here a patio of the timber and these small trails here for the machines. And then 5 years later, we start losing under canopy vegetation. 10 years later, you lose 50% of the canopy, and 10 to 15 years later, you lose 90%, and then you start seeing fire scars. That's exactly a very high risk because the forest evolved in millions of years without fire. Microclimate in the forest floor is extremely wet. Only 4% of solar radiation reaches the forest floor. Very wet, 26 degrees temperature, over 70–80% humidity. So when there is a lightning strike, ignited fire does not propagate. Now we see forest fires in this degraded land propagating for kilometers. So this is something we also should consider in doing this tipping point modeling intercomparison. So this is the areas with forest degradation. This is another 17%. Of course, this is very close to areas of deforestation, but that's something we have really to consider. As Patricia mentioned, 30 years ago with our deceased friend, astronaut Pierre Sellers and Shukla, we produced the hypothesis of savannization. That was one of the first papers dealing with that. And basically, that was only deforestation. No, we did not do any climate change. That was 1990, 1991. But just this is forests, and then we remove the forest, replaced by degraded pasture, and then we ask what would be the equilibrium vegetation, and then this all southern Amazon would have a savanna-like climate, would be consistent with a savanna with 6 months of dry season. But of course, there are hundreds and hundreds of studies since 1990. In particular, I just highlight this one published in The Guardian a few months ago, and showing the Amazon may be very close to tipping point, Stahl et al., published last year. A very interesting study that looked at, with the current climate, this green area is very stable for rainforest with a long wet season, but then with projected climate change future in the end of this century, only you are 100% sure the forest will remain only near the Andes here. And at the end, the concave shape of the Andes is the reason why you have a mechanical convergence zone, because the trade winds coming from the Atlantic go here and will move around the Andes. So there's a convergence zone. That's why we have 3 to 5 meters of rainfall here today. And that area would continue always be a forest, because you, even with an increase in temperature, you have sufficient rainfall. But all these other areas could become a savanna. So this is very interesting warning of a tipping point coming very soon. On the other hand, a very recent study published recently, looking now with the Hadley Center CMM Earth system model with the relatively high emission scenarios, RCP 6.0 from CIMI 5, look at not only 2100, but then up to 2500, much longer time scale. And this model in particularly does not see a total tipping point by 2100. You see here over 6% remaining forest, the broadleaf tree forest, and but starting to have a more bare soil. But when you move to 2500, almost all of the Amazon will become a semi-desert area, very, very less than 500 millimeters of rain a year. I'm not going to say this is going to happen. I'm just saying it does not see immediate tipping point in this model calculation. But this is only climate change. And let me just show one study we carried out in 2016, in which we looked at these 4 anthropogenic drivers: elevated CO2, which is positive for the rainforest, climate change, global warming, deforestation, forest fires. We did not take into consideration forest degradation. So basically, when we only look at deforestation only, when there is a 40% deforestation, then we lose almost 50% of the forest. So this is a tipping point for only deforestation. And when we have climate change, 20% deforestation, fires, and the positive effect of CO2 all considered together, then for the 3 RCP emission scenarios, we have 50% of the forest, and the RCP 8.5, 40% of the forest. So this would be by 2050. So that would be a tipping point in this calculation would be reached. And this is the how the forest, and this is in the model, this vegetation model that we have, it would, the seasonal forest, this light green, and the savannas would move, and the remaining only 50 to 6% of the forest in the Western Amazon. So basically, theoretically, this is pretty much what we see, this climate vegetation equilibrium. We have this stable equilibrium today with forest covering all of the Amazon, but also it would be stable, a 2-state equilibrium, forest in the west, a savanna-like in the central east, southeast, and then with enhanced frequency of drought and forest fires. 2021, we had the strongest drought in history in 100 years of data in central, southern Amazon and southeastern South America. So if that happens, that would increase the stability of this degraded ecosystem. Also, the CIMIP 6 is showing, this is terrifying. You know, when I saw this paper, I was very concerned. Globally speaking, the Amazon, northern South America, is the place with the highest frequency of heat waves and droughts. In any scenario, 1 degree, 1.5, with 3 degrees, very high frequency. It's impossible to keep the forest under these scenarios. And of course, in terms of this domino effect of the interconnectedness of the tipping points, we are already seeing unfolding this increase or decrease in this slowdown of the Atlantic meridional overturning circulation here, with increased subtropical temperatures, ocean temperatures in North Atlantic, and that induces droughts here in the Amazon. So this is, and of course, this slowing of the Atlantic meridional overturning circulation has to do with the melting of the ice sheets in Greenland. So this is the interconnectedness, and all of you certainly know this very well, but we may, let me just say now, show you briefly, I will run very quickly here. Observations, I want just to tell you that we are really seeing unfolding these risks of the tipping point. It's not only modeling calculations any longer. Based on 35 years of observations, field experiments in the Amazon, we really compare with degraded pasture. That's 90% of the deforestation in the Amazon is converted into pasture land, which becomes degraded over time. But basically, what we see, the stronger water recycling of the forest due to a rougher surface, deeper rooting system, as I mentioned. So we have 3.5 millimeters a day, higher in the dry season, as I mentioned, a smaller vapor pressure depth in the surface air, cooler and more humid, maximum temperature 30 degrees. Over pasture, smoother surface, very shallow rooting system, much higher vapor pressure depth, warmer and drier, 1.5 to 3 degrees warmer, maximum temperature 35, much less water recycling, and we are already seeing unfolding 10 to 20% reduction in rainfall, particularly during the dry season. So these observations, and I just put here the degraded savannas, degraded pasture, because that's most of the land use change. What we are also seeing, increasing frequency of droughts, 2005, 2010, 2015, 16, 2020. 3 out of these 4 related to Atlantic, tropical North Atlantic warmer temperature. Very concerning, very concerning. 40 years, we are seeing the dry season is becoming 3 to 4 weeks longer in southern Amazon, 2 million square kilometers from southern Peru all the way to the Atlantic. This is already happening. This is not a future projection. In only 40 years, almost 1 week per decade. Also, another study showed that this onset of the rainy season is becoming even more delayed in heavily deforested areas, as we might expect. Also, studies are showing the forest is becoming, as I mentioned, because of degradation and warmer temperature, much more susceptible to fire. Fires, even in years of normal rainfall, fires are increasing. Another study by NASA group show a very concerning item. This is vapor pressure deficit. It's tremendously increasing. The air is becoming hotter and drier. Perhaps one of the most concerning data comes from this study. This is, in fact, the 2019. There is a mistake here. In these red circles here, the dry season is becoming drier, hotter, and what we are seeing is mortality rate of wet climate taxa of 3 species is increasing. So this is happening already. It goes from Peru, Bolivia, Brazil, and even northeastern Amazon. So this is one sign of what's going on in the Amazon now. That's why perhaps we are very close to a tipping point. This is another study showing with the rainfall, the hundreds of places where people measure the tree diameters. And so we are seeing the Amazon, the carbon sink is decreasing over from 1990s to the present significantly. The Science Panel for the Amazon has made a summary of that and seeing the Amazon is becoming much weaker carbon sink, only 220 million square kilometers. Here you see the green is sink, the red is emissions. And also, there's a paper published recently in Nature. I just want to focus, this is based only on aircraft measurements of CO2, methane, and CO. So just to make a difference between when the air is mixed with biomass burning. But this green here is just the natural source or sink. This has nothing to do with burning. So basically, you see this is sink in this area of the Amazon, sink, but the southeastern Amazon has become a source. This is the forest. This is only the measurements of the photosynthesis minus respiration. And of course, that has to do with what I showed, the increased mortality of trees. The deforestation is 26% here. Precipitation in the dry season is 24% and 2.5 degrees warmer during the dry season. So this just to show this area of the Amazon has become a carbon, the forest has become a carbon source. Of course, the Amazon stores around 100 billion to 200 billion tons of below and above soil carbon. So is the Amazon going to become a carbon source or sink? This is really a very important question. Not needless to say, if this large portion of that ends up in the atmosphere, forget about the Paris Accord, targets. And this is for IPCC Working Group 1, our AR6 report launched in August, and we see a scenario of the Amazon, most of the tropics becoming a carbon source, including the Amazon. And of course, there are many studies that the native tropical rainforest can become a seasonally dry tropical forest or a savanna, open canopy degraded, or closed canopy degraded secondary forest. All those possibilities are open, but when this is the question we have to ask because of this feedback, positive feedback, tree loss, less evaporation, decreased rainfall, longer dry season, less humidity, more fires, more tree loss. So this is really putting high speed towards reaching the tipping point, which has to do with also with the larger scale the climate change associated with increased temperature and increased frequency and intensity of droughts. And also this is one experiment in the southern Amazon in which forest fires were allowed for a few years, and then 6 years after the last forest fire, that's the resulting open canopy degraded ecosystem. This is being seen in a lot of places in the Amazon. So this is probably what would be the future of the Amazon after crossing the tipping point. So I'm finishing. I just want to say also, even if we cannot say for sure, the forest has already reached the tipping point, and we have to really, I mean, this is one key message from the science panel for the Amazon. We have to reach zero deforestation, forest degradation in this southern portion of the Amazon now, immediately, and then get into zero deforestation degradation in all of the Amazon before 2030, as COP26, at least countries, including most Amazonian countries except Venezuela, signed the agreement. Then we have to start a huge forest restoration, particularly in southern Amazon, and even before 2030, having restored tens of millions of hectares. And then we also have to develop innovative standing forest bioeconomy. Those are some key conclusions of the science panel for the Amazon. Thank you very much for this opportunity.
Thank you, Carlos, for your brilliant exposition of what are the latest summary of what we consider the Amazon tipping element. So it's not only on the projection, it can come early as possible as 2050, and also observed data has also been showing this. So it's very alarming results. But now if you want to, have questions for Carlos, just place on the KU box, because now we're going to introduce you to our second speaker, nonetheless, highly important. It's also a pleasure and an honor to introduce Peter. So he's a professor, Dr. Peter Cox. He's a professor of climate system dynamics in mathematics at the University of Exeter. He also a lead author on the last three assessment reports of the Intergovernmental Panel on Climate Change, and besides being absolutely highly cited as an author in the geoscience. So Peter, the floor is yours, and I couldn't say again, what a honor.
Thank you, Patty, and thank you, Carlos. I'm going to try and share my screen now. Where are we? Yeah, so great pleasure to be here, folks, especially following Carlos, who's been teaching me about, I got this wrong way around, haven't I? Can you see my full screen here, folks? Patty?
Not full screen.
You just swap the slideshow, Peter?
Oh yeah, you should play.
Okay, I can't see that. Oh yeah, like that. Better now? No.
No.
Worse now?
No, now you cannot see it.
Let's try this. Right, let me go back.
Well done.
There you go.
We're nearly there, Tim.
Well
Right,
done.
thank you, folks. And thank you, Carlos, as I said. So Carlos has been informing me about the Amazon and has been really consistent in his messages about the Amazon. I've fluctuated a bit more, and I'm going to explain why on this, although I am now of the opinion that there are real new reasons for concern on this. I'm going to give some early results from the CMIP6 models, which are the latest models from the IPCC, using the IPCC report. And I'm going to especially be using results from my colleagues, Paul Ritchie and Isabel Parry, who's a master's student at Exeter. Paul Ritchie is a postdoctoral researcher who've been doing some analysis on this. But I'm going to start a bit with the history of this, at least my history of this, in the context of concerns and the results we've got recently on this. So it's going to be a bit back and forward on this. Okay, so originally I got concerned about this because we did some coupled model experiments. These were coupled climate carbon cycle projections with a model called HADCM3LC, which was basically the HADCM3 model that Carlos showed. This is strange. And what we found was that the forest in this model essentially died because of climate change. There was no direct deforestation in here. So everything I'm going to talk about here is not the multiple stresses that Carlos talks about, but just about climate change. And what we found in this model was that the forest sustained itself up to the current day roughly, and then there was a feedback process where the Amazon dried out, got hotter, and the forest started to be lost. There was reduced moisture recycling, and then we ended up with essentially a savanna state, or even worse than that. So those sort of things Carlos was speaking about. And I spoke about this a lot at the time. There were reasons why we subsequently thought that that might not be a very likely outcome, thankfully. One of them was that this particular model, compared to the models of its similar generation, which was called C4MIP or CMIP3, produced the largest reduction in rainfall by quite a long way. And the second one that was really a key thing for me is that we also found that the variants of that model that produced big dieback produced variability, year-to-year variations in the CO2 growth rate that were not consistent with what we see from the Morne-Lau record. And I'll explain that very briefly. This is a key reason why I think some of the most extreme results we got at that time were not likely to be true. So this is what we call an emergent constraint. In other words, it's a relationship between what models predict for the future and something we can measure in the current day. In this case, it was essentially the interannual variation in the growth rate of atmospheric CO2. This is work that I did with colleagues in 2013, and Sabrina Wenzel did it in the later CMIP5 models, and has subsequently done it in the CMIP6 models, and it appears to be robust to those model generations. The basic idea is shown here. And I hope you can see my cursor. So basically the CO2 emissions have been going up. This is an old picture now. The atmospheric CO2 growth rate doesn't go up as smoothly or as quickly. Doesn't go up as quickly because CO2 is being removed by the land and ocean. But the variability here that you can see, that's the difference between the black line and the blue line, is essentially variability in those natural sinks, and especially variability in tropical forest uptake. So this variability we see in the sink is actually indicating variations in tropical land uptake, and in response largely to El Nino events and volcanic events. And you can see that if you plot them against each other. So in black here, we've detrended the CO2 growth rate, and we've got a variation in that about a trend. You can see high values, for example, in 97, 98 with the big El Nino and other El Nino events. And then we've plotted in red the tropical temperature anomaly. And you can see they're quite well correlated, apart from periods like in 91, 92, when we had a situation where Pinatubo went off and changed the dynamics of the system, basically by introducing other factors that affect the CO2 growth rate. So basically we know that. And what we found in 2013 was that if we took the models that were available at the time and we plotted the amount of carbon lost from the tropical land per degree of warming in the tropics, which is this y-axis, against the sensitivity of the CO2 growth rate that they simulated, then we found there was a straight line. So basically models that had a very negative impact of climate change on the tropics, for example, because of Amazon forest dieback, also had very large variations in the CO2 growth rate from year to year. And as I showed you just now, there's actually an observational constraint from the Mauna Loa records that tells us roughly what that is in this green bar here. So we could sort of tell that the models that were producing dieback at that time were not consistent with the variability we saw in the CO2 growth rate, because they're all down in this lower right corner. And that led me to believe that the sort of dieback we were seeing in those shocking results in the year 2000 thereabouts were not very likely. So all well and good, a bit happier then, but a lot's happened since. So as Carlos pointed out, the tropical forest, especially Amazonia, is not just suffering climate change, it's also suffering anthropogenic deforestation, and that's gone up recently. Carlos showed that also the inventory-based observational evidence of a reducing Amazon carbon sink, and he showed this before, but I want to just come back to it. This is amazing data from rainfall, where basically tree diameters are measured to calculate carbon uptake over many years by lots of incredible effort on the ground. The net uptake here, you can see at the top, this is a Bow paper from 2000, by the way, is dropping through time. And you'll see in the second plot here that this is not because tree growth rates have been going down, which is what our original model results would have suggested was going on, but actually because the tree mortality rate is going up. It may be for the reasons Carlos said, that wet trees that are adapted to the wet conditions of the Amazon are suffering more mortality. So actually, we are seeing some of that reduction in the land carbon sink, in the carbon sink in the tropics in Amazonia, but it's not for the reasons we were finding originally. It's not because of reduced tree growth rates, but because of increasing mortality. And then we started to look at the latest models. Now, CMIP5, the previous generation of the models, you could say that we weren't quite sure about the Amazon rainfall change, I think, at least in response to climate change. So huge uncertainty. I think there's much more agreement in the latest CMIP6 models. This is an ensemble mean that Paul Ritchie produced of rainfall and soil moisture change. This is a high CO2, 4 times CO2, so we've given it a big kick. But you can see a much greater agreement in rainfall reduction, especially in the north of the basin, and also of soil moisture. And that I'm going to come back to in a minute, because we're seeing other evidence from observational data and also from model outputs that's leading to a drying that we can see in what's called the evaporative fraction, which is the amount of the energy at the surface that comes back as evaporation. And Isabel Parry, the master student that's been working with myself and Paul, has been using an algorithm that looks at abrupt changes in these models, which are all models that have got vegetation dynamics in them. Sorry, this figure's a little bit small, but you can see in red the areas where there are detected abrupt downward shifts in vegetation carbon. And there's a threshold for that. It's a 2 kilogram per carbon at least a 2 kilogram carbon per meter squared change within 15 years, and an abrupt change that makes up for 25% of the total change. So it's a big kick downwards. And you can see that these are quite prevalent in these models. Rather ironically, in the lower right, or the second from the lower right, is UK ESM, which is the latest variant of the Hadley Center model, which is the only one that now doesn't produce any dieback in this scenario. I just want to show you one example of this. I've got at the bottom of here an HTML link to a very old clip of Carlos teaching me about the importance of fire, but I'm not going to show it, although it is interesting to look at because he's been telling me this for a long time. I only just realized. So this is from the GFDL model. And the interesting thing about this is it contains elements of a new type of dynamic, possibly a more realistic dynamic than we've seen before. And that's basically because the model actually has fire in it now. So you can see at the top, rainfall reducing significantly in this simulation, temperature going up. And you see in green, the tree cover, which goes along quite happily at about 70%, and then drops in these big spikes you can see, which we believe to be fire events in the model. This model has interactive fire. And there's a recovery actually in tree cover, you can see after the first, but not a recovery in vegetation carbon. So we presume that the bigger trees have been wiped out and being replaced by smaller trees that are getting wiped out before they can get big. And so you get a transition to a savanna in this case. It's a very much more realistic looking scenario, if you like, than the ones we were getting in the early models. And there's an increase in variability that's a response to the change in land cover. So you can see more variable, longer term variations in precipitation when you get to the drier, less tropical forest state, more like a savanna. Isabel has also been looking at the regions that these regions. So Northern South America is the region that contains a lot of the tropical forest, the Amazon rainforest. And the South American monsoon is another region that we've looked at. This is what we see in the NSA region, North and South America. So if you look at these models, you do see a range of responses in terms of the total vegetation carbon here, some up, some down. I think in these large scale averages, you wouldn't say there was an abrupt change anywhere here, possibly in the yellow model a little bit, which I think is the Thai ESN model. But if you look at if you try to diagnose where these abrupt changes are occurring, there are lots of them. And they increase in their likelihood as you increase global warming, which is what's shown on the x-axis here. We pretty much see this in all models, bar one, such that if you look at the compiled models, the fraction of the area that sees an abrupt change goes up continuously with global warming until you get to the point where essentially their models aren't going any further than that in this scenario. So we see good evidence that just because you don't see abrupt changes in the large scale mean variable, it doesn't mean you're not seeing very abrupt changes locally, which of course would be very damaging and have very significant impacts. What we find, which is very interesting about this, and this is another reason for concern, is that in each of these areas where we see an abrupt change, and here's an example from GFDL at the top that I showed you before, the fire regulated transition. Here's one from North CPM, which is slightly more gradual, like the original dieback we saw in the HAD-CM3LC, and another one in Thai ESM. In all cases, if you look on the right-hand side, the amplitude of the temperature variability within year, so hottest month minus coldest month, is going up and significantly. And that is consistent with there being a longer and more intense dry season. As Carlos said, this is the reason for concern. This is the thing that seems to be very clear when I come to the reason why I think that is. But what it means is that we might have in this temperature seasonal cycle amplitude, which is relatively easy to get from meteorological data, a sort of warning of drying and therefore of the possibility of dieback. So here is from the compiled models, here's a histogram that Isabel produced. The red areas here are ones where the trend in vegetation carbon is down and there's an abrupt shift downwards of a significant magnitude. And you can see as the sensitivity of the seasonal cycle to global warming gets larger, so in other words, per degree of global warming, we get a more intense dry season, most likely, then the red areas, which are the places that have a tipping point downwards, an abrupt change at least, become more and more larger and larger fraction of the total number of points. So the purple areas here have got no abrupt change detected. The red areas have got what we might consider to be a downward abrupt change consistent with a dieback. And in actual fact, if you look at the ratio of the purple to the red, you can plot that as a function of this sensitivity of the seasonal cycle to global warming, and it goes up very significantly. It's a minimum risk at 0, which is what you might expect, and a maximum risk when the seasonal cycle is getting very large as a function of global warming, which we believe is consistent with the dry season getting longer and more intense. And interestingly, Paul Ritchie looked at the ERA reanalysis, so essentially the ECMWF reanalysis of best estimate of climate since 1980. And he finds in each of these regions a similar trend, red in the seasonal cycle, so upward trends in the amplitude of the annual cycle in temperature, near surface temperature. And if we look in this model at the evaporative fraction, so that's the evaporation divided by the total available energy at the surface, which goes down when the system's getting drier, then in all of these regions, the evaporative fraction is going down at the same time the temperature seasonal cycle is going up. And that, again, is consistent with a more intense dry season. And I saw this paper just yesterday on Twitter, which is where I find out all my news these days. They're consistent with longer and more intense dry seasons. This paper here, which I haven't read properly yet, in Climate Dynamics, just came out, looks at tree ring oxygen isotopes and infers that the Amazon dry season has been getting more intense and longer over the last 40 years. And that's very consistent with the things that Carlos was saying. Now, if we look, as Paul has done, in models over the next out to 4 degrees of global warming, we see an extension of this trend. So again, in red here, we've got the temperature seasonal cycle going up. So as we think, probably more intense and longer dry seasons, and the evaporative fraction dropping in blue. And we have in here, in the plumes, the results from the models that I showed you before. In fact, a larger range of models than I showed you before. And then we've got reconstructions based on HAD-CRU-T data set. And again, showing that the HAD-CRU-T data set also contains consistent evidence of an increasing temperature seasonal cycle, consistent with drying, which we can see also in the models. And so there is something quite robust emerging out of this, which is a drying and most likely an extension of dry seasons. Okay, so I'm going to stop now because we've got time for discussion. So the latest CMIP6 Earth system models do show large-scale loss of forest carbon under climate change. Well, do not show large-scale loss of forest carbon under climate change in a coherent way, like we saw in early models, but they do show many abrupt local changes of forest carbon. So this is taking large-scale averages would lead you to miss many of these abrupt changes. And I would argue they're abrupt. The importance of abrupt changes for impacts is not diminished by the fact that the averages are not abrupt. Abrupt changes, if you live in an area that's undergoing abrupt change, like suddenly getting a fire, are very significant indeed. We find that abrupt changes are more likely in grid boxes where the seasonal cycle of near surface temperature increases most strongly. So where the temperature cycle is going up most with global warming. The increasing temperature seasonal cycle is correlated with reducing annual mean evaporative fraction, which is a sort of indicator, a general indicator of drying, and seen consistent with more intense dry seasons. And the temperature seasonal cycle in Amazonia has been increasing with global warming according to observational data sets, and importantly is projected to increase further with global warming. And that seems to imply greater risk of abrupt downward shifts in vegetation carbon. And after that, I thank you very much for your attention. Thanks, folks.
Thank you, Peter, for your talk. And again, there are few results that are alarming, and then also giving more and more evidence of where we are with the climate change. So I think now in the Amazon, so I think now we would, switch to the questions from the public. I don't know, Tim, do you want to start? you said you would be monitoring the Q&A.
Sure thing. Well, we've got a really lively Q&A going. Thanks for the fantastic talks, both of you. Let's start with Carlos. There was just one or two clarification questions. So an anonymous attendee, Carlos, was asking, you quoted a 50% loss of the Amazon, and their question was whether that was on top of the 20% deforestation or whether the 50% was the total. That's it.
Yeah, that experiment is just you cut down the forest, 20% deforestation, and then you abandon the agriculture. You try to see whether the forest will be restored, regenerate naturally. So that's the answer. So the 50% is the total area. So the forest would not regenerate in most of the deforested areas.
Thank you. And Peter, we've got a specific question from Thomas Hickler. Did all of the CMIP6 models include deforestation scenarios based on something called the LUH2 land use change scenarios? Or maybe only half or so of them managed to do that in the end, or were different land use change scenarios used? So I think it's really about, is there a consistent representation of land use change going on in the climate models?
So in the results I showed Thomas, there was no land use change. They were just 1% per year CO2 rise experiments, up to 4 times CO2. So we're just looking at greenhouse effect on forests. I think, I hope that where we did SSP scenarios, that land use change was applied consistently. I think it probably was, but that wasn't what we were showing you there. We were showing you very idealized runs. So I was specifically looking at the climate change effect.
We've also, Carlos, got some quite specific questions. People really interested in this question of your proposal, which I support, that we're going to need a massive regeneration of the forest activity. And someone is asking, how is the forest recovery being carried out? Is it aiming to recover the biodiversity you mentioned that allows the forest to be more resistant to the droughts? Yeah, there's some more elements to the question, but I guess it's really trying to pick apart what you were recommending there.
Yes, one suggestion I have also to Peter and to many of you is how to model human set fires, because even the results that Peter showed are very worrying. But in addition to land use, that you take only deforestation, but there is a fact that over 95% of fires in the Amazon are not lightning strike ignited fires. They are human-made fires. So we have, Peter, to see how to model that, because I think, as soon as we start really saying, okay, this degraded vegetation is very risky to fires, but they are human-made fires. So I think if we add the risk that human-made fires introduce to these abrupt changes in the whole system, I think we might have a much better view. I don't know any, because in our model calculation, we consider fires, but not really the way we are seeing unfolding now. If you look at the NASA fire monitoring system, they showed in 2020, 40% of all of the fires happen in forest areas, not in agricultural land. So I just want to say, really, we have to find a way to model these human-made fires. This is very different from Western US or Siberia or Canada or Australia, in which most of the fires are lightning strikes. In the Amazon, 95% is human. We have to introduce this other land use practice. And I think it will, as soon as we introduce in models, it will really show the risks are even larger. So about the question, yes, the science panel for the Amazon, a very clear message is not that it's going to be achievable, but at least we are saying over 200 authors. We are saying zero deforestation in Southern Amazon, zero forest degradation immediately, and then getting to zero deforestation, degradation, fires all of the Amazon before 2030, and also huge, large-scale forest restoration. 23% of the clear-cut areas in the Amazon have been abandoned by agriculture, by livestock farming. So there is some level of regeneration, which is a good idea, but unfortunately, deforestation is increasing. We are having a continued increase in deforestation rates in the Amazon in the last 7 years. So anyway, let's say one response to COP26 from Amazonian countries would be really to have forest restoration, large-scale forest restoration, as a global challenge. This is not only something that Amazonian countries, and I don't think Amazonian countries have all the resources, the financial resources to restore, let's say, 50 million hectares or 100 million hectares, because, well, 50 million hectares, it's possible, because it costs about $3,000 to $3,000 per hectare for forest restoration. So we really need to have a global response, and we need financing. Amazonian countries need, I would say, more than $150 billion of financing to start a large-scale forest restoration.
Peter, you want to come in on?
Yeah, just to come back on that point that Carlos made about forest fires. Forest fires are not in all of these models. I showed you an example from GFDL where they are, but in that case, they would not have had human set fires. They would have been just natural fires that burnt because of conditions being right for fires. So I think you're right, Carlos, that fire modeling is becoming up the agenda big time, because of course we can see fires all around the world. And the people that work on fire modeling do look at human factors as well as lightning strikes, etc. What is clear is we're in many locations of the world, we are entering a regime where fires previously were rare and now going to become quite an important dynamic, and fire management and fire impacts can absolutely key. So I think the models that are now introducing fires are finding some pretty horrific feedbacks that we hope are unrealistic.
I'm going to switch to some bigger picture, some questions that are in the chat as well. So Elizabeth Holland's got a great question around what's the possibility of cascading impact of Amazon deforestation on other tropical forests around the globe mediated by climate change? So I guess that could be allusion not just to the fact that you're adding carbon to the atmosphere, but that historically modeling studies that deforested the Amazon showed these teleconnection effects to other bits of the climate. Don't know if either of you are welcome to comment on that. Maybe Peter first.
I mean, there are certainly teleconnections from forested regions. Carlos is an expert on this because of all the stuff that was done on prescribed deforestation. I think especially in Indonesia, it's been seen actually, teleconnections to there. The Amazon, of course, is recycling a lot of water. So if you take it out, you should expect tropical circulation to be changed a lot. And I'll hand over to Carlos because he knows a lot more about that than I do.
Well, one thing I think, it still deserves a lot of studies, but of course it was raised by the Princeton University people there using GFDL model, published 2020. But actually, there were much earlier publications during the LBA years. Still open, but I think it's worth really doing more studies. But GFDL model, when they have simulations of Amazon deforestation and reduction of rainfall in the Amazon, 20–30% reduction, there is atmospheric wave propagating to the north, associated with, let's say, the annual rainfall in the Amazon is 2.3 meters. And then when you clear the forest, that reduces 30%. And then you have a higher pressure, anomaly because of this reduction of rainfall, because of course latent heat from the clouds lower the pressure. That's why you have a lower pressure over the Amazon. And then when you do these calculations, so there is this wave, stationary wave originating in this higher pressure anomaly over the Amazon, propagating to the northwest and reaching the California. And this study, and actually some other studies with Jeff Delmodel, they indicated that with full loss of the forest and reduction of rainfall, and most models, six models show that you might have this stationary propagating stationary wave, and then the California would become even drier. So I think, of course, we need many more studies to see whether the change in larger scale circulations due to reduction of rainfall by 20–30% would really imply communications to the, like El Nino, La Nina, stationary waves propagating at global scales. I think we need more studies, but it's interesting to see, at least to be warned that losing the forest may have implications, global implications. And of course, as I mentioned in my presentation, getting a forest dieback scenario, extreme scenario in this century, means losing something like 300 billion tons of carbon dioxide over, some of these studies show 30 to 50 years for the tipping point to be crossed. So that's 300 billion tons of carbon dioxide. And then the 1.5 degree target, which is 50% likelihood with 400 billion tons, only losing the Amazon, you got three-fourths of this maximum emission possibility. So I just also want to say, not a direct meteorological connectivity with tropical Africa or Southeast Asia, but also, of course, with the emission scenarios, the tipping elements of emission scenarios.
Thank you. So I'm just going to note that we've filled a fascinating hour already. We're delighted that many of you are hanging on, and we're going to just keep going for up to another 25 odd minutes with the discussion to try and get through the questions. I'll hand back to Patty in a second, but we're both thinking that the next question that really deserves an answer on the chat is one that's coming in from Diana Liverman, who's asking, in terms of possible recovery of the Amazon, how much reforestation is needed, and how long is the time it would take to step back from a potential tipping point? It's really a question also about, is there an irreversible legacy here? So at which point do we get into the irreversible territory? I might let Diana come in. That was the short version of the question, but have maybe Peter first, because I know you've been publishing with Paul Ritchie on, maybe the optimistic view that sometimes we can step past the tipping point before all hope is lost.
Yeah, so thank you for the question, Diana. And I think the issue about overshooting thresholds applies less to fast tipping points like the Amazon, but it also means the timescale to get back is a bit shorter. But it looks like, from the stuff that Carlos was showing and things we've done previously, that where there is a long-term trend, it's probably associated with the warming of the North Atlantic. Carlos, I think that was what you were showing, and that's a longer-term process because, of course, the ocean is slow to respond to changes in what we do now because it's storing heat over an integrated period. So I think there was an issue about definition of irreversibility, as you know, Tim, and strict irreversibility versus effective irreversibility. But in the IPCC report, we just spoke about effective irreversibility, which is really about whether the change in one direction was fast compared to the change to go back. And that is true if your change is being driven by something that's slow. And in the case of tropical Atlantic, it is slow. So I think it's not truly irreversible. I don't think, but it is effectively irreversible on the timescale that we think about policy. Yeah.
Yes, I think, I still have some questions. It may be just a coincidence that we have had 4 extreme droughts, 2005, 2010, 2020, related to warmer tropical North Atlantic. And I do not disagree with Peter that, the changes in the Atlantic meridional returning circulation is a very slow process. But on the other hand, even a small warming of the tropical North Atlantic is inducing those droughts. Peter, I'm not sure we can say some of this much higher frequency of these 4 droughts that we've seen in the last 16 years, they are related to any natural variability. So it might be somewhat related to natural variability, or it might also be a small increase in North Atlantic temperature is inducing not only stronger hurricanes in the Caribbean, but also inducing this much higher frequency of droughts in the Amazon. So perhaps, it's a nonlinear relationship between a very small increase, 0.5 degrees, one degree in the tropical North Atlantic induces droughts. You don't have really to increase the temperature much more than that. That's one question. Also, the second point that you raised, I also think we still don't have an answer, which is because we are seeing the dry season becoming longer over 1/3 of the Amazon basin, southern Amazon basin, 2 million square kilometers. Let's say even if we get to 0 deforestation, 0 forest degradation, 0 wildfires, and then large scale, large scale restoration projects, whether, what we are seeing in this increasing vapor pressure deficit in reducing evapotranspiration, is this new restore forest, is it going really to reverse that? I'm not saying it will reverse. That's a question that's still open. And also, of course, some of these effects are large scale. This increasing vapor pressure deficit, it's not only related to less evapotranspiration, it's also related to stronger El Niños and La Niña events in the Pacific. So I'm not sure whether restoring large areas would be sufficient to fight back this disruptive change, which is unfolding, that the data is showing. It's not only a model calculation. So I'm not sure. But of course, I mean, what I'm saying is 0 deforestation, 0 forest degradation, 0 wildfires. This is a moratorium. We in the science panel, we are saying that the key message. However, when you look at there is an analogy with COP26 main conclusions. Getting 1.5 degrees, reducing 50% emissions by 2030 compared to 2020 to 2019. All those things are necessary, but when you look at the way people are still using fossil fuels, etc., it seems to be almost impossible. So I'm not very optimistic about the results of COP26. And also, unfortunately, I'm not very optimistic about the moratorium, the agreement from COP26 of 0 deforestation global forests, because we are seeing unfolding in the Amazon countries, this organized crime, almost all these fires, deforestation, degradation is all controlled by organized crime. It's very difficult to think we will really reach this 0 deforestation degradation by 2030.
So I might jump in now with some of more human dimension or policy-oriented questions that I think it's relevant. Both of Peter and Carlos has been talking about the reasons for concern with the Amazon in the context of a warming climate. Has also talked about the tipping elements that we have, like an event that might not happen, that a lot of variability on or unpredictability of a possible dieback. But what we are observing is this incredible struggle or what we say limits to adaptation among the population, among especially indigenous people and so on and so forth. So and we know the challenge that the modeling community might have to really pick it up on the domains of institutional arrangements and also governance strategies. So where I'm trying to get is like on the IPCC and some colleagues on the working group too, we have been talking a lot on what are the adaptation limits and to what extent we are already witnessing like some elements of human or social tipping points associated with the ecological tipping points in the Amazon. So I'm just like getting your opinion or how, we know that hard adaptation limits are imposed when specific thresholds associated with the ecological systems are reached. So for instance, coral reefs by 1.5 warm degree will be a completely collapse. And likewise, we're talking about the Amazon forest. So I want to just see what, Carlos and Peter has to say, and also as a way of stimulating people on the modeling community and the youth of like thinking through how we can navigate these domains of kind of like a gloomy scenario that we are observing on the modeling and also on the observation of impacts in the Amazon. So to any of you, Peter and Carlos, I'm sure you guys both have a strong or opinion, well-informed opinion about it. And then I come back with some of the questions on the Q&A.
I'm not sure any of my opinions are well formulated, Patty, but I'm happy to give them anyway.
Okay.
So, I mean, I think one of the reasons we are interested in forewarning of tipping points is, of course, that we hope that you might be able to do something about them if you've got enough forewarning. In this case, where the large-scale effects are changing, you'd have to do something to counteract that if you couldn't do something about the large-scale change. But I can imagine that being true locally, and we're seeing local tipping points going on in the models rather than large-scale ones. So you could imagine, irrigation as one crude limit of it, or you could imagine replanting, or you could imagine planting different species, or you could imagine assisting a change in the forest to a more resilient form for the new climate. And I think as long as we've got forewarning, there's a chance that we make the right decisions collectively. So at the moment, I would say the key thing is to know, especially for these fast tipping elements like forest dieback, whether we could get enough warning to know when we need to do something in a remedial sense that it doesn't necessarily involve the whole world acting together. I'd love it if we do. But I think we might need to get ready for the fact that might not happen. That might sound a bit dark, but I think there are things that might be done more locally anyway. So there's an issue about keeping the pressure on the international negotiations, but it looks to me like we're very likely to overshoot 1.5. And how far can we overshoot? There's a question in the chat from Matteo about this. It's really key here to know how much the risk goes up with the overshoot, basically, for these sort of effects. And that means you need to know how close you are to the tipping point. And that means you need reliable and robustly measured indicators of that. And that's one thing I would focus on. But Carlos might have an idea about how we change the world.
Yeah, well, I think there is a lot of younger scientists in this audience. I hope they will do better than my generation. we did warnings. We always did warnings, but we are not our generation of scientists. We're not really. I'm not blaming on us, but we did not succeed in terms of when you look at today. 30 years after 1990, we have 6% more greenhouse gas emissions compared to 1990. So, and the first IPCC report was back there. So anyway, Patricia, I'm not an expert on biodiversity, but of course in the science panel for the Amazon, we had a very nice analysis, many chapters dealt with biodiversity. And of course, the Amazon has, in plant and animal species, has not less than 10%, perhaps 10 and 15% of all biodiversity. And of course, as also we know how important the biodiversity is for maintenance of the rainforest. And it's not really, if we cross the tipping point, I don't think we know whether there is any way for saving hundreds of thousands of plant and animal species. I don't think, still perhaps science can find ways, but I don't think we really, today we know it will be a mass extinction, particularly, more than 30% of these species are highly endemic, particularly in western, southwestern Amazon. So yes, I mean, that's why we are always warning, most of us, including Tim, who were the first one really to put in together all these tipping elements for decades already. And really, we try really to say, let's try to avoid with 1.5 degrees warming, with zero deforestation, all tropical forests, all global forests, because I'm not sure we have solutions for increasing resilience of species. Humans, yes. However, when you talk about indigenous peoples, it will be also very hard because they've been living for thousands of years in this system. And of course, I mean, in thousands of years, there is adaptation, because when you go to mid-Holocene, southwestern Amazon was a savanna, part of eastern Amazon. There was a connectivity of savannas from Venezuela all the way to central Brazil. In the city, today, the city of Santarém was a savanna. So of course, when you talk about thousands of years, the indigenous people, they've been in the Amazon for 12,000 years. Of course, I mean, they will adapt. But when you talk about, crossing a tipping point in a few decades or so, it's going to be really very hard for the indigenous people to find ways of increasing resilience, because they develop an economy, a science, indigenous science, very interesting. They use hundreds, thousands of forest products. They, we know, the 84% of the soils in the Amazon are very nutrient poor, except near the Andes because of erosion there. You have soils, nutrient-rich soils, but most of the Amazon plains are very poor, and still the indigenous peoples develop sustainable, productive agriculture in the so-called dark earth. They create this dark earth over thousands of years. So it's very hard really to say or to expect these populations will quickly increase their resilience. It's very difficult. That's why, we keep always saying, let's do the best we can to avoid the tipping points. 1.5 degrees warming, global warming, forest restoration, zero deforestation, and zero forest degradation. It's a new development pathway. This is also the science panel for the Amazon. We have 13 chapters dealing with this new sustainable future for the Amazon. So we have put together a large number of scientists, economists, ecologists, educators. They're putting together very good, practical, immediate policies to revert deforestation and degradation, and maintaining indigenous peoples, maintaining knowledge, traditional knowledge. So, but we have really, it's very similar to the climate change challenge. We have, 10 years to reverse emissions. We have less than 10 years to get to zero deforestation degradation in the Amazon.
So that's great, Carlos. Thanks for your answer. So I'm wrapping up with a question that, as we present, we have found the problem, as you and Peter are mentioning, that's like the generation of new model community that's coming up, but also what we can do in terms of policy domain. We know that we are having, in as much as climate change now, certain agreements, and when it comes to the table of how much finance we're going to get, likewise, how much governance and structure will be in place to make sure that we avoid this abrupt change. We were avoiding getting to the tipping point and avoiding more suffering and economies that will collapse. So there is a question from the public, I think is directed to Carlos, but I would extend it to Peter as well as a wrap up kind of question: how to build pressure that change the Brazilian policies in the case of the Amazon, and I would include also in the global scale right after Glasgow COP26. What are your ideas in terms of collective action and at the global scale? I know Peter already mentioned being skeptical about, but what is your idea and impressions of so many years of experience working on this topic?
Yes, this is a difficult question. Well, when you talk about Brazil has 63% of the Amazon forest domain, highest rates of deforestation, degradation. You see, I see sometimes two opposite points here. When you talk about fossil fuel combustion, this is a big industry, the largest industry in the planet, but by and large, it's legal business. It's legal. So, you have to quickly switch to renewable energy, electric vehicles. But in the Amazon, on the other hand, most of these activities, land use change in the Amazon, is all illegal in all Amazonian countries. So this is not really, because people, I was reading a newspaper article this morning about a growing Chinese movement in China with Chinese population. They say, we want to burn fossil fuels because, that's our well-being. The developed nations burn a lot of fossil fuels and they are rich because of that. So you see, this is a difficult issue. But the Amazon, really, it's not a philosophical question like this one put forth by Chinese people, people from India as well. They are raising these issues. In the Amazon, the economic activity related to deforestation, forest degradation is ridiculously low. Does not make any sense economically. The cattle ranches are so low productivity cattle ranches. It's ridiculous. I mean, let's say it's one head of cattle per hectare. One head of cattle per hectare. Productive livestock farming in Brazil is 5 heads of cattle per hectare. So it's all criminal. It's organized crime. Unfortunately, now there are not scientific studies, but there are some evidence that even the drug trafficking organized crime is associated with this illegal market of land grabbing, timber, selective logging. 80% of the selective logging, the timber industry in the Amazon is illegal. So in a way, different than fossil fuel, which is much harder to switch the speed of increasing fossil fuel use, in the Amazon is really to bring a democratic state, a legal framework, because it's really much easier to increase productivity in sustainable agriculture. So it's doable. It's doable. But of course, I mean, you have really to and people, still there is a discontinuity, a disconnectivity between the desire of people when polls are carried out, particularly in Brazil. 96% of Brazilians are in favor of the protection of the Amazon forest. They want to maintain the forest. But when you see the way the agribusiness is expanding, illegal mining, everything illegal, so it's a small number of criminals doing a lot of harm. So really, the Amazonian countries should put together a law enforcement, a democratic transition to law enforcement. We had a very good experiment in Brazil in 2011-12. We got the lowest deforestation rates in history since 1970s. And the agricultural productivity doubled between 2005 and 2014. And the Amazon deforestation, Brazilian Amazon, reduced 75%. So basically, in a way, it's a big challenge, but it's different than fossil fuel. It's really fighting crime, fighting this small number, because when you talk about there are 43 million people living in all Amazonian countries, well, the criminal organizations may have 20,000, 30,000 people. So really, it's a war against crime. I'm not saying it's easy, because organized crime is becoming very, very strong in Amazonian countries, connecting drug trafficking with land grabbing, with timber, the selective logging, illegal selective logging, all those things, illegal mining. We are just seeing in the media in Brazil, in the planet, all this illegal gold mining in the Madeira River in the last few days. So all those things are exploding. And in a way, if the Amazonian countries decide really to implement democracy, implementing the will of the people who want to maintain, to preserve the Amazon, to favor sustainable agriculture, we could really get to zero deforestation, forest degradation, different than the speed in which we're going to replace fossil fuels. So we could do that in less than 10 years. We have the good experience in Brazil from 2004 to 2012. So, however, we need the political will. We are lacking the political will. So we are hoping, in Brazil at least, we have elections to 2022, and we hope we're going to see a major change in federal government, because the current federal government in Brazil is people call the Brazilian president the tropical Trump, and he is in favor of this type of destruction of the Amazon, quote unquote, development model. So we hope really to change things in Brazil in the election next year, but also the other Amazonian countries have to do that. It's not as simple. Even the only Amazonian country president who has a political discourse in terms of sustainability is Colombia, Ivan Duque. But deforestation is increasing in the Amazon, all illegal, all crime. So this is the big battle we have to face to combat the illegalities in the Amazon. If we succeed, and we can succeed in 10 years, then we are going to get to close to zero deforestation.
Thank you, Carlos. Eloquently put. I'm afraid that's almost taking us out of time, but I must give Peter a chance to give his thoughts there before I wrap it up.
Thank you very much, Carlos. Thank you very much, Tim and Patty and everyone who's organised this. I mean, I do think someone just asked me on the chat, how do you stay positive when we don't seem to have done anything about it in the 30 years I've been talking about it? And the reason is, I think we've had a tipping point, in the sense that I'm optimistic that the public's sort of the grassroots push now for action is stronger than I've ever seen before across the world. And the Fridays for Future and the Greta Thunberg and all the stuff associated with that is giving a greater impetus for action and policy focus on climate change than I've seen in my 30 years in the research. So even though we haven't yet turned it round, it feels like this is the way you do it, which is that you talk about it, you get people informed, and then the body of people that want it done push it over. And I think that's happening. So we're sort of seeing a tipping point, or we've seen one, and it's just a question in a way now of riding it a bit, because it's a tipping point in the right direction for once. Thanks.
Nicely put, Peter. So we're a little over time, but I mean, we thank both of our speakers warmly, and Patty as well, for helping chair to address this crucial issue. So literal hand claps from me, but I'm sure virtual hand claps from over 100 people who've stuck with this vital discussion. So thanks everyone for engaging. Peter just put it very eloquently. I think if we just keep having this discussion as widely and broadly, and as Carlos says, as democratically as we can, that's surely going to help. We have further tipping element focused discussions like this coming up. The next one that's definitely happening will be on the permafrost around on 17th of January next year, 4 p.m. on Central European time, whatever time that is with you, wherever you are in the world. We also have one that we had to postpone on ice sheet tipping points. So we'll send some circulars around as soon as we get that rescheduled in the diary. And there's a wonderful discussion going on the Miro board, which I think will stay live after this session. And we also have, for the specialists still hanging on in the audience, we're trying to bring together tipping point model into comparison project activity. So if you want to be part of that and aren't already, just reach out to any of us and we'll point you in the right direction. So yeah, let us all redouble our efforts, I guess, to get the message out there, and hope we can turn it round from kind of bad tipping points for the Amazon to some positive social tipping points to preserve, restore, regenerate this crucial, vital harbor of life and life support on our planet. Thanks a lot.
Thank you. Thank you very much. Bye-bye.